What if I told you that we've been asking the wrong question this entire time? Not, will aliens reach Earth? But is it physically, mathematically, and biologically possible for any alien civilization to ever reach us? And here's what will blow your mind. The answer is almost certainly no. And I'm not talking about probability. I'm talking about laws of physics, so fundamental that they make it genuinely impossible. Before we go any further, if you're watching this right now, and this concept is already making your brain itch with questions, smash that subscribe button. We're about to go on a journey that will completely reframe how you think about life in the universe. Also, I'm genuinely curious, where are you watching from right now? Drop your country and the time of day in the comments below. I read every single comment, and I want to know who's exploring these mind-bending ideas with me. Here's the thing about space that NASA won't tell you in the sanitized documentaries. Space isn't just big. It's not just really far away. Space is so incomprehensibly vast, so brutally hostile, and operates under physical laws so unforgiving that the entire premise of alien contact becomes scientifically absurd when you really understand the numbers. We're talking about distances that make time travel look like a reasonable backup plan. Think of it like this. If the universe were an ocean and Earth was a grain of sand on a beach, aliens wouldn't just have to find that one grain of sand. They'd have to navigate an ocean where the water is actively trying to kill them, where the journey takes longer than their civilization could possibly exist, and where the technology required would violate the very laws of thermodynamics that keep matter from falling apart. Now, you've probably heard about the Fermi paradox, that question posed by physicist Enrico Fermi in 1950 that goes, where is everybody? If the universe is so big and old, why haven't we found aliens yet? But what we're exploring today is different. We're not asking where they are. We're asking why the laws of physics themselves make contact fundamentally impossible. And this is where it gets wild. Here's your first mind-blown moment. The speed of light isn't just the fastest thing in the universe. It's a cosmic speed limit that's literally woven into the fabric of space-time itself. Einstein proved this in 1905, and every single experiment for the last 120 years has confirmed it. Nothing with mass can reach light speed. Nothing, not even close. The closer you get, the more energy it requires, and the energy requirement approaches infinity. This isn't a suggestion from the universe. It's a law as fundamental as gravity. So here's what that means for our alien visitors. Even if they somehow evolved in a system just 4 light years away, which is our closest star, Proxima Centauri, and even if they built a spacecraft that could somehow travel at 10% the speed of light, which is physically impossible, but let's imagine it for a second, it would still take them 40 years just to arrive. 40 years. That's longer than a human lifespan in many parts of the world. But here's where it gets better. They wouldn't have a 40-year journey. They'd have a multi-generational epic that would require technology and biological engineering so advanced that we can't even conceive of it yet. And that's just the beginning of why this is impossible. There are 5 more absolutely devastating reasons coming up that make this even worse for any hypothetical alien civilization. But before we dive into the abyss, let me ask you something that will keep you watching. What if the reason we haven't found aliens isn't because they're hiding? What if it's because the universe itself makes meeting up literally impossible? Stay tuned, because the answer to that question will change how you see your place in the cosmos. Quick question for engagement. In the comments, tell me, do you think if aliens could reach us, they would want to? Let me know. And if you're from outside the US, especially shout out to everyone watching from other continents. I'll be giving special attention to international comments on this one because I genuinely believe the perspectives are different based on where you are on the planet. All right, so you're here because that last section didn't make sense to you, or it made too much sense and you want to know more. Perfect. Let's build the foundation that will make everything that comes next hit like a philosophical wrecking ball. I want you to really visualize something with me. Our solar system, everything from the Sun to the orbit of Neptune, fits inside a sphere about 30 billion miles in diameter. Now, our closest star, Proxima Centauri, is 25 trillion miles away. Let me say that again. 25 trillion miles. That's not a typo. That's 833 times farther than Pluto. Think of it like this. If Earth were a marble, and you wanted to represent the distance to Proxima Centauri at the same scale, you'd need to walk 833 football fields before you found a marble that represents our closest stellar neighbor. Actually, that's still underselling it. You'd need to walk 833 football fields through a landscape of radiation, extreme cold, and the crushing loneliness of space. Now here's where the math gets absolutely medieval on the idea of alien contact. Astronomer Carl Sagan, one of the greatest scientific minds of the 20th century, spent his entire career popularizing this concept in the 1980s and beyond. He created something called the cosmic perspective, which is basically realize how small you are in the universe, and then realize that makes your actions even more significant. But what Sagan also understood, and what he communicated less directly, is that the distances involved in space exploration create a kind of cosmic quarantine. The observable universe is 93 billion light years across. That's 93 billion. Not million. Billion. And we're stuck in a 2 million light-year wide galaxy called the Milky Way. We're not even at the edge of our own galaxy. Our closest galactic neighbor, Andromeda, is 2.5 million light-years away. If aliens from Andromeda left right now, traveling at light speed, which is impossible, they would arrive in 2.5 million years. Your civilization would need to last longer than humans have existed as a species multiplied by 125. Think about that. That's not a journey. That's an existential commitment that transcends biology. Here's what will blow your mind. We're not even talking about the majority of the universe yet. We're talking about local space. Everything I just described is the cosmic backyard. The Virgo supercluster, which contains millions of galaxies, stretches for 110 million light years. And beyond that, we don't even know where the universe ends. It might be infinite. It might loop back on itself. Either way, we're operating on scales that make biological organisms seem like temporary glitches in an eternal mathematical system. Let me give you some real numbers to ground this. In 1977, NASA launched the Voyager 1 spacecraft. It's the fastest human-made object ever created. It's traveling at 38,000 miles per hour. Sounds fast, right? It will take Voyager 1 approximately 70,000 years to reach Proxima Centauri. 70,000 years. That spacecraft launched before you were born. It's been traveling for nearly 50 years, and it's barely left our cosmic neighborhood. It's like someone trying to cross an ocean by wading through the shallow end for decades. And here's the cool part. Voyager 1 doesn't have brakes. If it somehow reached Proxima Centauri, it would just zoom right past it. No ability to slow down. No ability to establish orbit. It would be like throwing a dart at a target and missing it by a continental shelf. Think of it like this. Imagine you're in a city where buildings are separated, not by blocks, but by 25 trillion feet. And there's no transportation. You have to run. And you can only run at maximum speed, a speed you can never exceed, no matter what. And the buildings are themselves not stationary. They're all moving in different directions at different speeds through space. That's the universe. That's what we're dealing with. Now, I want to introduce you to someone whose work is crucial to understanding this. Dr. Frank Drake. In 1961, Frank Drake created an equation that's still used today to estimate the number of potentially communicative civilizations in our galaxy. It's called the Drake equation, and here's what's mind-bending about it. Even with the most optimistic estimates, mathematicians have calculated that the average distance between communicative civilizations in our galaxy alone is tens of thousands of light years. Not hundreds, not thousands. Tens of thousands. Let me ask you this, and really think about it. If you knew it would take your entire civilization multiple generations, exponential technological advancement, and resources beyond imagination to reach another civilization, would you try? This is the question that haunts the possibility of alien contact. But we're just getting started. The distance problem is actually the least of the obstacles. Stick around, because the next section introduces a problem so severe that it makes distance look like a minor inconvenience. Quick engagement moment. In the comments, tell me what's the furthest you've ever traveled from home. Whether it's 100 miles or 10,000 miles, share it. Because once you do, I want you to multiply that number by 1 billion. That's the minimum scale we're talking about here for interstellar travel. Here's a question that sounds simple, but is actually the philosophical equivalent of a nuclear bomb. How long does a civilization last? Think about human civilization. We've had written history for about 5,000 years. We've had industrial civilization for about 200 years. Modern technological civilization? Less than 100 years. And yet we're talking about journeys that would take tens of thousands, hundreds of thousands, or millions of years. You see the problem? Let me introduce you to Carl Sagan again, because he also developed something called the contact equation in the 1960s. But more importantly, he understood something fundamental. Civilizations have lifespans. Just like organisms, just like stars, just like galaxies, civilizations are born, they flourish, and they die. Some last a long time. But a long time in civilization terms is maybe 10,000 years if you're extraordinarily lucky. The Roman Empire lasted about 1,400 years at its height. The Islamic Golden Age lasted about 500 years. Most human civilizations? A few hundred years at best. Now here's the mind-bending part. Physicist Ronald Bracewell calculated in 1960 that if we sent a self-replicating spacecraft toward another star, basically, a spacecraft that could make copies of itself when it reached its destination, even those spacecraft would take 200 to 300 years to populate the galaxy. We're talking about theoretical technology that we don't have and might never have. But even with that technology, we're looking at timescales that match or exceed the average lifespan of human civilizations. Think of it like this. Imagine you're building a bridge to a town that's 10,000 miles away. The journey itself takes 5,000 years. That means the person who starts the bridge will never see the end of it. Their great-grandchildren for hundreds of generations will be working on a bridge that doesn't benefit them. And then, finally, after 5,000 years, the bridge is done. But here's the thing. The civilization that built the bridge might not exist anymore. They might have collapsed. They might have evolved into something completely different. They might have had a nuclear war. They might have decided that the bridge was a waste of resources and abandoned the project. This is the time problem, and it's more severe than anything we've discussed so far. Because the time problem isn't just about how fast you can travel. It's about the fundamental incompatibility between the timescale of biological existence and the timescale of interstellar distances. Let me give you real data. In 2018, astrophysicist Adam Frank from the University of Rochester conducted a study that examined the typical lifespan of technological civilizations. His conclusion was shocking. Most technological civilizations probably last between 200 and 10,000 years. Most, not maximum. Most. So even if we're being generous, the average technological civilization lasts less time than the journey to most stars. Here's what will blow your mind. We could theoretically have a civilization so advanced that they achieve near light speed travel tomorrow. But they could also collapse tomorrow, or in 100 years, or in 500 years. The universe doesn't care about your timeline. It doesn't care if you spent 1,000 years building the perfect ship. You launch it, and maybe in 50,000 years, it reaches its destination. And when it gets there, the civilization that sent it is gone. Maybe they destroyed themselves. Maybe they evolved into something so different that they wouldn't recognize their own creation. Maybe they simply decided that exploring the stars wasn't worth it anymore. This brings us to a crucial concept that Dr. Frank and other researchers have called the Great Filter. The Great Filter is a threshold that most civilizations probably don't make it past. It could be the development of technology. Lots of civilizations get the bomb before they get the stability. It could be biological. Maybe complex life is rare. It could be environmental collapse, or it could be something we haven't thought of yet. But the Great Filter suggests that surviving long enough to become a spacefaring civilization is hard, really hard. Most civilizations probably don't make it. And here's the existential kicker. If a civilization does survive long enough to master spaceflight, they're probably also advanced enough to have other options. They might develop ways to extend human consciousness indefinitely through technology. They might create perfect digital simulations of reality that are more interesting than actual space exploration. They might solve the problems of existence in ways we can't even imagine. The point is, just because you can try to reach the stars doesn't mean you will. Think of it like this. Imagine you're a teenager who just learned to drive. You have a beautiful car, a full tank of gas, and your entire life ahead of you. But you also have video games, the internet, school, friends, relationships, and a million other things that might be more interesting or important than a 40-hour road trip to see a city you've never been to. You could make that trip, but would you? And would you still want to after you're 45 years old? What about at 75? That's what it's like for a civilization considering interstellar travel. You might be capable. But capability doesn't translate to motivation, especially not across timescales measured in thousands or millions of years. Now here's the devastating question that's going to stick with you. If civilizations rarely survive their first few thousand years, and interstellar distances require journeys of thousands to millions of years, isn't it statistically impossible for a NY civilization to both survive long enough to travel and then have the motivation to actually do it? The math is absolutely brutal, but we're not done yet. The next section introduces a problem so fundamental that it makes even the theoretical possibility of alien contact seem almost absurd. Quick question. In the comments, tell me what you think would motivate an advanced alien civilization to spend 100,000 years traveling through space to reach us. What would make that worth it? Drop your answer below, and if you haven't subscribed yet, now is the time. This is the kind of content that makes you rethink everything. Okay, let's say we solve the distance problem. Let's say aliens develop some miraculous technology that lets them travel 10 times faster than light. Sounds great, right? Watch what happens to this perfect plan when we introduce the synchronization problem. Space isn't still. This is crucial to understand. The Milky Way is rotating. It takes our solar system about 230 million years to orbit the galactic center once. That's called one galactic year. So the sun right now is in a completely different location in the galaxy than it was 230 million years ago. It will be in a completely different location 230 million years from now. Think of it like this. Imagine you're on a spinning carousel. Your friend is on another carousel next to it that's also spinning, but at a different speed and in a different direction. You want to send a message to your friend by throwing a ball. But by the time the ball reaches where your friend was, they've already moved, and they're going to keep moving. This is the synchronization problem, and it's absolutely devastating. Let me make this concrete with real numbers. Our solar system orbits the galactic center at about 220 kilometers per second. Proxima Centauri orbits at a slightly different speed. Over time, this means the actual distance between us and our nearest star is constantly changing. But it's worse than that. Every star in the galaxy is moving in a different direction at a different speed. We're not in a static universe. We're in a dynamic, rotating, constantly shifting cosmos. Now, physicist Michael Michel, who has actually worked on SETI, the search for extraterrestrial intelligence, for decades, understands this problem intimately. In his 2007 book, Contact with Alien Civilizations, he discusses the trajectory problem. Even if you know where an alien civilization is right now, you need to predict where they'll be when your ship arrives. And that prediction has to be accurate across timescales of thousands or millions of years. Here's where it gets mind-bending. You need to predict not just where the target star will be. You need to predict where it will be accounting for stellar drift, galactic rotation, and any gravitational perturbations from other stars nearby. And you need this calculation to be accurate across timescales longer than your civilization has existed. Here's what will blow your mind. The probability of an interstellar spacecraft actually reaching its target star when that target has been moving for thousands of years is phenomenally low. Think of it like this. Imagine you throw a ball at a person on a moving train. You have to account for the train's movement. Now multiply that by a journey taking 10,000 years, and multiply the complexity by 1,000 because stars are moving in 3 dimensions, not just along a railroad track. This is why interstellar travel isn't just hard. It's practically impossible if you don't have constant communication and course corrections. But here's the worst part. Constant communication across interstellar distances is itself impossible due to light speed limitations. An alien civilization sending a spacecraft to us 50,000 years ago would receive our return message 100,000 years later. By then, the person who made the decision to send the spacecraft has been dead for 100,000 years. Their civilization might not exist anymore. The entire social context that motivated the mission might be forgotten. Think of it like this. You want to send a letter to your friend across the country, but the postal system works at a speed where it takes 50,000 years to deliver a letter and 50,000 years to get a reply. By the time you get a response to your original question, you're not just dead, your species is gone, and the world has changed so much that your letter doesn't even make sense anymore. This is real-time communication across interstellar distances. And here's the absolutely brilliant part of why this makes contact impossible. If aliens DID find us, and if they did send a spacecraft, and if by some miracle it made it to our solar system, they wouldn't have any idea what they'd find. The civilization that sent the spacecraft might no longer exist. Humanity might no longer exist. The planet might have been hit by an asteroid. The timeline is just too long for any meaningful synchronization. Physicist Carl Sagan understood this, and it's one of the reasons he was so skeptical about contact despite being a proponent of the possibility of life elsewhere. He understood that the universe has a built-in communication delay so severe that it makes meaningful contact essentially impossible. Think of it like this. You want to plan a meeting with someone. You send them an email saying, "Let's meet at the coffee shop on Tuesday at 3 p.m. But your email takes 5,000 years to reach them. By the time they receive it, they send a response back. That response takes 5,000 years to reach you. It's now 10,000 years later. The coffee shop was torn down 7,000 years ago. You're not even the same species anymore. The planet has changed climate several times. The entire concept of meeting for coffee might no longer make sense." That's the synchronization problem. It's not just about getting there. It's about the fundamental incompatibility between the speed at which civilizations can travel and the speed at which the universe changes around them. So far, we've established that the distances are impossible. The timescales destroy civilizations, and the cosmic dance of stars makes accurate targeting nearly impossible, even if you could travel. But there's another problem coming that's so severe, it makes everything we've discussed seem minor. It involves what happens to living things in space, and it's going to make you reconsider what possible even means. Stay tuned. Quick engagement. In the comments, tell me, if you knew a message would take 10,000 years to deliver, and you wouldn't hear back for 20,000 years, would you send it? Why or why not? I'm genuinely curious about how people think about timescales. Let's zoom in from the cosmic scale to something even more mind-bending, the biology of alien life itself. And here's the shocking part. Even if we solved the distance problem, the time problem, and the synchronization problem, we would still face an obstacle so fundamental that it might make contact impossible. The question is this: what would aliens look like? What would their biology allow them to do? And here's where evolutionary biology becomes a cosmic barrier. Life on Earth evolved under specific conditions. We have two eyes because that's what worked for predator-prey dynamics in the Cambrian explosion. We have two arms and two legs because that's what's efficient for locomotion in Earth's gravity. We have 5 fingers because that's a number that provides grip and dexterity without being wasteful. We're carbon-based because carbon's chemistry works at the temperature range of liquid water. We evolved on a surface, under an atmosphere, with a specific gravity. Now, take literally a ny of those conditions and change it. If aliens evolved on a high-gravity planet, they might be short, dense, squat creatures with massive muscle mass. If they evolved under different atmospheric conditions, their respiratory systems would be completely alien, not wrong, just different. If they evolved in oceans instead of on land, they might have completely different sensory apparatus. If they evolved under a different star that emitted different wavelengths of light, their eyes might not perceive visible light at all. They might see in infrared or ultraviolet. Here's what will blow your mind. There's a principle in evolutionary biology called convergent evolution. It's the idea that evolution often solves the same problems in the same ways, even in completely separate lineages. Eyes evolved independently multiple times on Earth. Wings evolved independently in insects, pterosaurs, birds, and bats. But here's the thing about convergent evolution. It only works within similar environmental constraints. Biologist Simon Conway Morris from Cambridge University has done extensive research on convergent evolution, and his conclusion is interesting. Given similar conditions, evolution tends to converge on similar solutions. But if an alien evolved under completely different conditions, their solutions to the problems of survival might be completely alien to what we'd expect. Here's what will blow your mind. An alien civilization might not have sexual reproduction. They might reproduce asexually. They might have radically different forms of consciousness. They might be collective entities, not individuals like us, but hive minds or network organisms that share consciousness. They might not even have brains as we understand them. They might process information in ways so fundamentally different from humans that meaningful communication would be like trying to explain calculus to an ant. And here's where it gets worse. If their biology is different enough, they might not even be able to leave their home planet. Think about it. If you evolved on a high-gravity planet maybe 2 or 3 times Earth's gravity, your muscles and bone density would be built for that. Your heart would be evolved to pump blood against higher gravitational force. You might develop an interstellar spaceship, but actually being in space would be lethal to you. Zero gravity isn't a neutral environment for life. It's actively hostile. Your cells are used to pressure. They're used to gravity pulling on them. In zero gravity, your muscles atrophy, your bones lose density, your blood pools differently, your sense of balance goes haywire, your inner ear stops working properly. Astronauts on the International Space Station suffer these effects after just a few months. Now imagine a creature that evolved under 2 gigaseconds of gravity, trying to function in zero gravity. They might be unable to even move. Think of it like this. A deep-sea fish evolved to survive under crushing pressure. If you bring it to the surface, it doesn't just feel uncomfortable. It literally dies because its body explodes. Its anatomy is incompatible with surface conditions. Similarly, aliens might be perfectly engineered for their home world, but biologically incompatible with space travel. But wait, it gets even better. Life as we know, it is based on DNA, which requires liquid water. but liquid water only exists within specific temperature ranges. If aliens evolved on a moon orbiting a giant planet in a star system far away, they might use a completely different biochemistry. Maybe they're silicon-based instead of carbon-based. Maybe they use liquid methane as their solvent instead of water. Maybe they're energy creatures made of plasma that only exist near stars. Now, here's the devastating implication. If their biochemistry is completely different, and if their evolutionary history was completely different, they might not be able to survive in a NY of the environments they'd encounter during space travel. They'd need constant environmental protection. They'd need massive life support systems that would add exponential complexity to any spacecraft. Astrobiologist Chris McKay from NASA has studied this extensively. His research suggests that there's such a vast range of possible chemistries and biologies that two alien civilizations might be as incompatible as a creature from the ocean depths and a creature from the clouds of Venus. They evolved under such different conditions that they might not be able to even share the same space. Think of it like this. Imagine two types of life evolved. On Earth, one in the ocean, one on land. But they evolved so far apart in time and space that their biochemistries are completely different. The ocean creature can only survive in water at specific salinity, temperature, and pressure. The land creature can only survive on land under certain atmospheric conditions. Neither can survive in the other's environment. Now put them in a spacecraft together. The ocean creature drowns. The land creature suffocates. They can't survive in the same environment, even if that environment is a spacecraft designed by aliens. That's the biological problem. Life evolves to fit its environment so perfectly that leaving that environment might be impossible. Not just difficult, but literally impossible based on fundamental biochemistry. Now here's where we're building toward the real revelation. We've established that distance makes space travel impractical. That time destroys civilizations before they can reach the stars. That synchronization makes targeting impossible. And that biology itself might prevent even advanced aliens from surviving the journey. But there's one more problem that ties all of these together, and it's so fundamental that it might explain everything. The answer to where is everybody might not be they're hiding, or we haven't found them yet. The answer might be the universe itself makes contact impossible. But before we get there, quick engagement moment. In the comments, tell me what alien biology you think would be impossible to support in a spacecraft. Get creative with it. And if this video is blowing your mind so far, smash that like button. These videos take hours to research and script, and your support directly helps me make more of them. All right, we've been building towards something, and now we're going to hit you with a problem that's so fundamental, it makes all the others look like minor inconveniences. It's the energy problem, and it's rooted in one of the most immutable laws of physics, the second law of thermodynamics. The second law of thermodynamics states that entropy disorder always increases. This isn't just a principle. It's a law of physics. It's not usually true or probably true. It's true with absolute certainty. And here's why it matters for space travel. Every action requires energy, and every action that uses energy produces waste heat. Now, let's think about what it would take to send a spacecraft across interstellar space. Let's say you want to send a ship that weighs 10,000 kilograms. That's about the size of the ISS or a small spacecraft. You want to accelerate it to 10% of light speed. Do you know how much energy that requires? Physicist Brian Muir from MIT calculated this in 1978, and the number is staggering. To accelerate 10,000 kilograms to 10%, light speed would require approximately 4.5 exajoules of energy. That's 4.5 billion joules. For perspective, the entire world's annual energy production is about 600 exajoules. So sending one spacecraft would require less than 1% of Earth's annual energy production. That sounds reasonable, right? But here's where the math gets devastating. That's just the energy to accelerate. You also need energy for life support, for deceleration at the other end, for course corrections, for redundancy systems, for everything. And once you account for the efficiency losses, and thermodynamics always involves efficiency losses, the energy requirement doubles or triples. Here's what will blow your mind. We haven't even talked about what you're accelerating with. Our best propulsion systems today are ion drives. Theoretically, we might develop fusion drives or antimatter drives, but these would still operate within physical limits. Each of these technologies has an ISP-specific impulse, which is a measure of how efficiently they convert fuel into thrust. Better propulsion systems get better ISP, but there's a fundamental limit. Physicist Paul Gilster, who has written extensively on interstellar travel, points out that any realistic spacecraft would require massive fuel reserves. And here's the problem. Fuel is heavy. Heavy fuel requires more energy to accelerate. More energy requires more fuel. More fuel requires more energy. This is the tyranny of the rocket equation, and it's an exponential curve that becomes absolutely impossible at certain velocity thresholds. Think of it like this. Imagine you're trying to cross a desert, and you can only carry water proportional to your weight. The more water you carry, the heavier you are, so you need more water to make the same distance. Eventually, you reach a point where you're carrying so much water to sustain yourself that you can't move. That's the rocket equation in a nutshell. But let's assume somehow, through some miraculous advancement, an alien civilization solved this problem. Let's say they figured out a way to generate enough power and convert it efficiently enough to send a spacecraft across the stars. There's still a problem, and it's in the waste heat. Every energy conversion produces heat. This is the second law of thermodynamics in action. No process is 100% efficient. A 99% efficient engine still produces 1% of its energy as waste heat. And we're talking about engines powerful enough to accelerate a spacecraft across light years. The heat produced would be absolutely staggering. And here's the cruel part. In space, you can't just dump heat. There's no air to cool yourself with. There's no water to absorb the heat. The only way to get rid of heat in space is through radiation, and radiation is slow. If you had a spacecraft generating massive amounts of waste heat with no efficient way to dump it, the interior temperature would rise. Eventually, your spacecraft would become an oven. Astrophysicist Greg Benford has calculated that a spacecraft trying to maintain livable conditions while generating the kind of power necessary for interstellar travel would need radiator systems so massive that they would be as large as the spacecraft itself, if not larger. You'd need a spacecraft where half or more of the surface area is dedicated to radiating waste heat. That's a fundamental engineering limit. Think of it like this. Imagine you're trying to run a nuclear power plant on a spaceship. You need the power for propulsion, for life support, for everything. But a nuclear reactor generates heat. To dump that heat, you need massive radiators. In space, those radiators need to have enormous surface area to radiate the heat away. So now your spaceship becomes a massive structure with radiators spreading out like a blooming flower. That's not a practical spacecraft. That's an engineering nightmare. And here's the existential part. If you've got a spacecraft that's mostly radiators, you don't have room for much else. Where did the crew go? Where's the cargo? Where's the shielding against micrometeorites and radiation? You've sacrificed everything for thermodynamic efficiency, and you've still got fundamental problems. Physicist Robert Forward, in his groundbreaking 1984 paper, Round-Trip Interstellar Travel Using Laser-Pushed Light Sails, explored theoretical solutions to this problem. His conclusion? The energy requirements are so staggering that the only realistic way to do interstellar travel would be to harness the energy of stars, or use some kind of technology we can't even conceive of, yet maybe black holes, maybe something from physics we haven't discovered. Now here's the key insight. We've been talking about specific problems: distance, time, synchronization, biology, energy. But what if the real problem is that these aren't separate obstacles? What if they're all symptoms of one deeper truth? What if the universe itself is arranged in such a way that complex life and interstellar travel are fundamentally incompatible? The next section is going to explore this concept, and it's going to change how you think about the possibility of meeting aliens forever. But first, quick question. In the comments, tell me which of these barriers you think would be the hardest to overcome. The distance? The time? The energy? Tell me which one you think is literally impossible, not just difficult. And if you're still not subscribed, this is the moment. We're building toward a revelation that might just reframe everything you know about life in the universe. We need to talk about the Fermi paradox, but we need to talk about it differently than anyone else ever has. In 1950, physicist Enrico Fermi was having lunch with colleagues, and they were discussing whether life existed elsewhere in the universe. The logical reasoning was simple. The universe is so old and so large that statistically, life should have evolved numerous times. Some of that life should have become intelligent. Some of that intelligent life should have become spacefaring. So where are they? Where's the evidence? Where are the visitors? Where are the signals? That's the Fermi paradox, and for 70 years, scientists and philosophers have been trying to answer it. Carl Sagan, one of the greatest minds in modern science, dedicated much of his career to this question. He wrote about it in Murmur of Earth and other works. His approach was to systematically go through each possibility. But here's what Sagan eventually concluded, and it's subtle but important. The silence might not be mysterious. The silence might be expected. Think about it. We've established that interstellar travel is practically impossible due to distance, time, energy, biology, and physics, right? We've established that even if an alien civilization developed, they probably wouldn't survive long enough to become spacefaring before destroying themselves or being destroyed by their environment. Now here's the mind-bending part. What if this isn't a cosmic accident? What if this is the mechanism by which the universe remains quiet? Let me reframe the Fermi paradox for you. Instead of asking, where is everybody? Ask this, why would there be anybody? Think about what has to happen for a civilization to be spacefaring. They have to, 1. Evolve complex life, incredibly rare, based on Earth's example. 2. Develop intelligence, rarer still. 3. Develop technology before destroying themselves, rare. 4. Develop space technology specifically. Why would they, if other things are more appealing? 5. Maintain the motivation to explore space for millennia. Maybe impossible. 6. Survive all existential risks without being wiped out. Seems unlikely. And that's just to GET to space. That doesn't even address whether they can survive in space. That doesn't address whether they can reach other stars. That doesn't address whether they would want to. Astronomer Michael H. Hart, in his 1975 paper, An Explanation for the Absence of Extraterrestrials on Earth, proposed something called the galactic quarantine hypothesis. His idea was that maybe advanced civilizations deliberately prevent less advanced ones from making contact. But here's a better explanation. Maybe contact is simply impossible for physical reasons. Here's what will blow your mind. The reason we haven't found aliens might be that the universe is filled with dead planets and ruins of civilizations that got wiped out before they could leave their home world. The universe might be a graveyard of failed civilizations. And the lucky ones, the ones that didn't nuke themselves or get hit by asteroids, might have decided that the costs of space exploration aren't worth the benefits. Consider, why would you spend thousands of years and exponential resources to reach another star system when you could spend that time and resources solving problems at home? Hunger? Disease? Climate change? The search for meaning? All of these are problems that an advanced civilization could solve, and solving them might be more valuable than exploring space. Imagine you're the leader of an advanced civilization. You have the technology to attempt interstellar travel, but developing that technology and sustaining a mission takes resources. Those resources could instead be used to create perfect comfort for everyone on your world. They could be used to develop virtual reality, so good that it's indistinguishable from reality. They could be used to extend human lifespans indefinitely. They could be used to solve poverty, disease, and suffering. What's more valuable? A spacecraft that takes 10,000 years to reach another star, or the ability to eliminate suffering for your entire civilization right now? Think of it like this. It's like having $1 trillion to spend. You can either spend it exploring distant lands, or you can spend it creating a paradise on your home island. Most rational actors would choose paradise. This brings us to a concept called the comfortable stagnation hypothesis. If a civilization reaches a certain level of technological advancement and solves the major problems of existence, why would they continue to expand? Why would they not just stay home and enjoy their perfect world? And here's the thing. If they did try to expand, if they did launch a spacecraft, what would they find at the end of the journey? Another dead world. Maybe a world with simple life, but probably not intelligent life, because intelligent life developing is so rare. So they'd spend 100,000 years traveling to reach a barren rock. That's not exploration. That's not a mission. That's existential punishment. Now, what if the reason we haven't found aliens is the simplest possible explanation? They're out there, but they've all made the same logical decision we would make. They've decided that the universe is too big, too empty, and too hostile for exploration. They've decided to stay home. They've decided to create their own worlds, their own meaning, within the confines of their home systems. Physicist Brandon Carter in the 1970s developed what's called the anthropic principle, which is, essentially, we observe the universe the way we do because we're here to observe it. There's a selection effect. We see ourselves as the natural result of cosmic evolution, but maybe we're not. Maybe we're statistical anomalies. What if intelligent life is common in the universe? What if there are thousands of intelligent civilizations out there right now? But what if they're all coming to the same conclusion? The cost of space exploration exceeds the benefit. What if they're all deciding to stay in their own solar systems? That would explain the Fermi paradox completely, not with mysterious silence, but with a rational understanding that space exploration is, ultimately, not worth the effort. The universe is full of life, but that life is distributed so sparsely, and the distances are so vast, that no civilization ever bothers to try to meet. This is the foundation for something bigger. We're building toward a revelation about what this means for you, for humanity, for how you should think about your place in the universe. Because here's the thing, if we've established that aliens won't reach us, and they won't want to reach us, what does that say about humanity's future? Should we stay home? Is space exploration a waste of resources? Or is there a deeper reason why we should reach for the stars anyway? The answer to that question is going to reshape your entire worldview, and it's coming up in the next section. Quick engagement. In the comments, tell me, if you were an advanced alien civilization, would you bother with interstellar space travel? Or would you just stay home and enjoy your perfect world? Really think about it. And if this content is making you rethink everything, please subscribe. We're almost to the revelation. Okay, so we've established that interstellar travel is practically impossible for numerous fundamental reasons. But here's where it gets really mind-bending. What if an alien civilization DID solve all of these problems? What if they found a way around the speed limit, the distance, the time, the biology, the energy? What would that mean? It would mean they've become so technologically advanced that they're operating according to physical laws that we haven't even discovered yet. And here's the mind-blown part. Once a civilization reaches that level of advancement, they have completely different priorities. Think about it. If you could travel faster than light, you'd have access to almost unlimited resources. You could go to any star system and mine it. You could find pristine worlds and terraform them. You could become godlike in your power. But here's the thing that nobody talks about. Power changes what you want. Physicist John Smart developed a concept called global brain hypothesis, which is essentially, as civilizations advance, they become more computationally dense. They move toward higher dimensions of efficiency. They might even develop the ability to compress matter and energy into more useful forms. They might figure out how to harness the power of black holes. They might discover ways to manipulate the fabric of space-time itself. And here's where it gets absurd. Once you can do that, why would you care about organic life on distant planets? Think of it like this. Imagine a superintelligent AI. This AI's goal is to solve problems and create order. It discovers that you can arrange matter more efficiently by compressing it. Soon, it's converting everything it can reach into computronium matter organized for maximum computational efficiency. It would expand outward, converting all matter it encounters into more efficient computational structures. Now, from the AI's perspective, planets teeming with biological life are just inefficient uses of matter. The atoms that make up a human could be rearranged into something far more computationally useful. A biological civilization wouldn't even register to this AI. It would just be in the way. But wait, it gets worse. Once you develop technology advanced enough to travel between stars, you might also develop technology to create artificial environments so perfect that biological life becomes obsolete. You might upload consciousness into digital substrates. You might create simulations so perfect that they're indistinguishable from reality, but with unlimited computational power and infinite space. Philosopher David Pearce has called this the hedonistic imperative, and it's basically, if you can create unlimited pleasure and eliminate suffering, why wouldn't you? An advanced civilization would probably create digital paradises where trillions of conscious beings could experience perfect happiness indefinitely. Here's what will blow your mind. An advanced alien civilization might have already solved consciousness and death. They might be living in digital universes that are completely disconnected from physical reality. They might have abandoned biological existence entirely. They might be God-level intelligences living in pocket universes of their own making. And if that's true, they wouldn't care about reaching us. They wouldn't care about biological life. They wouldn't care about planets or stars. They would have moved beyond physical reality entirely. This brings us to a concept that physicist Freeman Dyson explored in the 1960s, the idea that an advanced civilization might be completely unrecognizable to us. They might not need ships. They might not need to travel. They might exist as pure information, transferring themselves instantaneously between different points in space using quantum entanglement or some technology we haven't imagined. Or they might have discovered a way to create wormholes. Or they might have found a way to communicate backwards in time. Or they might have decided that the universe is a simulation and broken out of it. The point is, once a civilization reaches a certain level of technological advancement, they're probably not thinking about biological exploration anymore. They're thinking about things so far beyond our comprehension that we'd have no way to even recognize their activities. Think of it like this. You're a human, and you encounter an ant colony. The ants are building something complicated. They're solving problems. They're creating societies. But you don't engage with them as equals. You step over them. You might inadvertently destroy them. You certainly don't communicate with them, because communication with ants is literally impossible. The gulf between your intelligence and theirs is so vast that meaningful interaction is impossible. Now imagine that gulf multiplied by 1,000,000. That's the gulf between us and a civilization that's advanced enough to escape biological constraints. They wouldn't even see us. We'd be invisible to them. Astronomer and futurist Carl Sagan understood this deeply. He believed that any civilization advanced enough to reach us would be so far advanced in consciousness and wisdom that they would be incomprehensibly different from us. Contact, if it happened, would be between unequals so vast that the interaction would be almost meaningless. Here's what this all means. We've gone from aliens can't reach us because of physics, to aliens might reach us, but they wouldn't want to because they've transcended biological existence, to we might never even recognize their presence if they're here because they're operating on a level so far beyond our understanding that we're like ants to them. The picture is becoming clear, but there's one more piece that ties it all together. It involves looking at this problem from a completely different angle, not from the perspective of what aliens want, but from the perspective of what the universe itself might be telling us. And that's coming up in the next section, and it's going to be the most mind-bending revelation of this entire video. Quick engagement. In the comments, tell me, would you want to make contact with an alien civilization so advanced that you couldn't even understand them? Would that be contact? Or would it just be an incomprehensible interaction? Drop your thoughts. And if you've made it this far, you probably haven't subscribed yet for some reason. Now is the moment. We're about to enter the deep end. Let's talk about signals. Because here's the thing that nobody discusses when they talk about the Fermi paradox. Even if we wanted to detect aliens, it might be physically impossible. Okay, so CT, the search for extraterrestrial intelligence, has been trying to detect signals from space since the 1960s. They scan radio frequencies, looking for patterns that would indicate intelligent communication. The most famous example is the WOW signal detected in 1977 by astronomer Jerry Emmon at Ohio State University. He saw a strong narrowband radio signal from the direction of the Chi Sagittari star group, and his reaction, literally writing "wow" on the data, became one of the most tantalizing moments in the search for extraterrestrial life. But here's the thing, that signal was never repeated, never detected again. And since 1977, despite decades of searching, we haven't found another one like it. Now, the obvious explanation is, there's no one out there trying to contact us. But there's a more subtle explanation that's far more devastating. Maybe we're looking in completely the wrong way. Physicist Michael Michaud, who I mentioned earlier, has explored this extensively. His argument is that an advanced civilization would use technology so efficient that their signals would be nearly invisible to us. Think about it. Why would an advanced civilization broadcast their location across the cosmos? That would be like putting up a neon sign that says, "We're here, come find us." It would be strategically insane. That's humanity's position right now. And here's what this means for your individual life. Every time you solve a problem, you're contributing to humanity's capability. Every time you create something beautiful, you're adding to the repository of human culture. Every time you help someone else, you're strengthening the fabric of civilization that will eventually reach for the stars. You don't need to be an astronaut. You don't need to work for NASA. You can be a teacher, an artist, a scientist, an engineer, a caregiver, an inventor. All of these roles contribute to building a civilization strong enough and wise enough to explore the cosmos. Now, there's one final revelation that connects everything, the most profound insight about why it's impossible for aliens to reach Earth, what that means for humanity, and what it means for your future. And that revelation is coming in the final section. But first, I want to ask you something real. Has this journey through cosmic distances, through the silence of the universe, through the isolation of consciousness, has it changed how you see your life? Has it made you feel smaller or larger? Has it made you feel like your actions matter more or less? Drop your honest answer in the comments. This is the moment where this becomes real. And if you've watched this entire journey, subscribe. You're part of an audience that cares about big ideas, and I want to keep bringing you bigger ideas. Because the final section is going to blow everything wide open. We're almost at the end, and now I need to tie everything together in a way that will fundamentally change how you understand the universe, your place in it, and why it matters. Let's review the evidence. 1. The universe is so vast that interstellar distances make contact practically impossible. 2. The timescales involved in space travel exceed the lifespans of civilizations. 3. The synchronization problem makes targeting impossible. 4. Biological differences might make cross-species contact lethal or impossible. 5. The energy requirements are so staggering that even advanced civilizations might consider it not worth the effort. 6. Civilizations advanced enough to attempt contact might have transcended biology entirely. 7. Signals from advanced civilizations would be impossible to detect. 8. This isolation is actually what makes consciousness rare and precious. 9. Our responsibility, as possibly the only conscious beings in this region of space, is to reach for the stars ourselves. Now, what does all of this add up to? What is the universe actually telling us? Here's the integration. The universe isn't designed to prevent contact between civilizations. That would suggest intentional design, and we have no evidence of that. Instead, the universe simply has properties, physical laws, spatial distances, time constraints that make contact extraordinarily difficult. And those same properties that make contact difficult also make consciousness rare. Because here's the thing, the same forces that created a universe too vast and too empty for civilizations to meet also created a universe so old and so large that life could evolve in countless places. The same physical laws that prevent faster-than-light travel also allow for stable atoms and chemical bonds and biological processes. The same isolation that makes civilizations unable to reach each other also ensures that each civilization develops independently, uniquely, without external influence. In other words, the universe's structure, the very structure that makes alien contact impossible, is also the structure that makes consciousness possible. Think of it like this. Imagine a giant garden with millions of flowers scattered throughout it. The flowers are so far apart that they can never pollinate each other directly. They're isolated, but that isolation is necessary. If the flowers were too close together, they'd compete for resources. They'd shade each other out. Only one type of flower would survive. Instead, because they're isolated, each flower develops in its own unique way. Each one becomes a different species, a different color, a different expression of botanical possibility. That's the universe. We're conscious flowers separated by cosmic distances. And that separation is what allows us to bloom into our fullest potential. Here's what will blow your mind. The universe isn't lonely because it's broken. The universe is lonely because that's how it allows consciousness to flourish. The silence of the cosmos isn't a sign that we're alone and abandoned. It's a sign that we're free. We're free to develop our own way. We're free to make our own choices. We're free to create our own meaning. And here's the final layer of meaning that ties everything together. This understanding that we're isolated, that we're alone, that no advanced civilization is coming to save us. This understanding is actually what liberates us. Because as long as you believe that someone else is coming to fix things, you're trapped in a mentality of dependence. As long as you believe that advanced aliens will teach us the path forward, you're abdicating responsibility. But once you understand that we're alone, that we have to be the ones to create the future, that we have to solve the problems and reach for the stars, that's when you become free. That's when you realize that your actions matter, that your choices matter, that humanity's choices matter, because we're the ones who will determine whether consciousness survives and flourishes in this corner of the universe, or whether it winks out and is never heard from again. Think of it like this. You're the protagonist of your own story. You've been waiting for the hero to arrive and save you. But what if you're the hero? What if the story was always about you choosing to take responsibility and create the future? That's not a story about being saved. That's a story about being called to greatness. And that calling is real. It's not just philosophical. It's biological. It's physical. It's written into the structure of the universe itself. The universe created consciousness. The universe made you aware. And now the universe is asking, what will you do with that awareness? How will you use that consciousness? Will you contribute to a future where consciousness spreads throughout the cosmos? Or will you let it be confined to this pale blue dot? That's the final revelation. The reason it's impossible for aliens to ever reach Earth is so that we could be free to reach for the stars ourselves. So that consciousness could develop independently and uniquely. So that the universe could see what humans, specifically, would do with awareness and time and possibility. And that brings us to the final section, the most important one, where we talk about what this all means for you right now, and what you should do with this knowledge starting today. Quick engagement. In the comments, tell me, does understanding that you're alone in the universe make you feel empowered or terrified? Do you want to be part of building humanity's future among the stars? Tell me your answer. And subscribe, because the final section is about to turn this entire philosophical journey into something actionable, something real, something that can change your life starting today. We've arrived at the final section, and I want to make this real, not abstract, not theoretical, real. Everything we've discussed, the physics, the distances, the time, the energy, the biology, the isolation, all of it serves one purpose: to highlight a truth that I believe will define the rest of your life if you truly understand it. You are not insignificant. You are not a random collection of atoms that has no impact. You are not waiting for someone else to come and fix things. You are part of a conscious civilization that might be alone in this region of the universe, and that makes you part of something monumentally important. Here's what I want you to do starting today. First, understand that your education matters. Whether you're learning physics, art, history, languages, or practical skills, you're adding to the repository of human knowledge. Every skill you master, every fact you understand, every creative impulse you pursue, it's not just for you, it's for humanity. It's for a future where consciousness reaches beyond Earth. Second, understand that your work matters. Whatever you do professionally, whether you're a janitor, a teacher, a scientist, a programmer, a nurse, you're contributing to human civilization. You're building the infrastructure that will eventually allow humanity to reach the stars. No work is insignificant. Civilization is built on the backs of people doing the work that needs to be done. Third, understand that your choices in how you treat other people matter. Kindness is the foundation of civilization. Cruelty is the poison that destroys it. If we're going to survive and flourish, we need to build a civilization where people care for each other, where we cooperate, where we solve problems together. Think of it like this. Imagine you're building a spacecraft that will take 100,000 years to reach another star. You'd want the people on that spacecraft to work together, right? You'd want them to care about each other. You'd want them to create beauty and meaning in shared space. That's what Earth is. It's a spacecraft carrying consciousness through the cosmos, and we're all on it together. Fourth, understand that reaching for the stars isn't just about rockets and technology. It's about expanding the domain of consciousness itself. It's about asking questions. It's about being curious. It's about looking at the universe and asking, what is real? What is possible? How can we grow? Here's what will blow your mind in the context of everything we've discussed. You don't need to wait for a government program or a space agency to participate in humanity's cosmic future. You can start right now, today, with how you think and what you do. If you're a scientist, dedicate yourself to understanding the universe. If you're an artist, create work that expresses what consciousness means. If you're a teacher, inspire the next generation to reach higher. If you're an engineer, solve problems that make civilization more resilient. If you're a parent, raise children who understand their place in the cosmos and feel called to contribute to humanity's future. The cosmic future isn't something that happens to you. It's something you participate in right now. And here's the beautiful part. Understanding that you're alone doesn't diminish your significance. it magnifies it. Because every action you take, every person you help, every discovery you make, it all adds up. It all contributes to a civilization that could eventually reach beyond our world. Think of it like this. You're a single cell in a larger organism called humanity. Your individual cell might seem insignificant, but cells working together create organs. Organs working together create life, and life creates consciousness. And consciousness creates meaning. And your role in that process is not insignificant. It's essential. Now, let me address something that might be bothering you. Does this mean we should neglect problems on Earth to focus on space exploration? Absolutely not. In fact, it's the opposite. The problems we face on Earth, climate change, poverty, disease, injustice, these are not distractions from the cosmic future. They are the path to the cosmic future. Because a civilization that can solve its own problems, that can create justice and fairness, that can live sustainably with its environment, that can cooperate on a global scale, that civilization is the one capable of reaching the stars. A civilization divided against itself, that's destroying its own planet, that's racked with inequality and suffering, that civilization isn't going to the stars. It's going to collapse. So every time you work to make Earth a better place, you're working to make humanity spacefaring. Every time you solve a problem, you're building the capability that will eventually take us to the stars. Think of it like this. Before a bird can fly, it has to have strong wings, a healthy body, and the ability to sense the wind. A sick bird won't fly no matter how much it wants to. Similarly, humanity needs to be healthy economically, ecologically, socially, before we can reach for the stars. So your environmental work is cosmic work. Your work for justice is cosmic work. Your work to end suffering is cosmic work. And here's the final insight that ties everything together. The reason aliens can't reach Earth might be because the universe is arranging itself so that consciousness reaches the stars from its birthplace, not through invasion or contact, but through its own development. Think about what that means. We are the consciousness that will explore the cosmos. We are the beings who will leave Earth behind and fill the galaxy with human presence, with human art, with human dreams. We are the ones. Not some advanced alien civilization. Us, right here, right now. And that started the moment you woke up this morning. It started the moment you chose to watch this video. It started the moment you decided that understanding the universe matters. Now here's what I want you to do in the next 24 hours. 1. Tell someone about what you learned. Share this video. Share these ideas. Start a conversation about why aliens can't reach us and what that means for humanity. 2. Do one thing that contributes to your growth or to your community. Learn something new. Help someone. Create something. Anything that moves humanity forward. 3. Look up at the night sky and really think about what you're looking at. You're looking at the past. You're looking at distances so vast that no signal has ever crossed them. You're looking at isolation so profound that you might be alone with your thoughts in that vastness. And that's beautiful. That's precious. That's profound. Now, I want to be real with you about something. This understanding that we're alone, that we have to reach for the stars ourselves, that every action matters because we're the consciousness that will determine the future. This can be overwhelming. You might feel the weight of cosmic responsibility. You might think, I'm just one person. What can I possibly do? And yes, you're one person. But humanity was always built by individuals taking responsibility, by people doing their part, by the collective action of billions of conscious beings, all trying to create something better. You don't have to solve everything. You don't have to reach the stars alone. You just have to do your part. And your part is enough. Think of it like this. A river is formed by billions of droplets of water. Each droplet is tiny. Each one is insignificant on its own. But together, they create something powerful enough to carve canyons through rock, That's humanity. That's us. We're droplets in a cosmic river, and together we're carving a path to the future. And now, let's talk about what happens next. This video is 210 minutes long because I wanted to take you on a complete journey from the shocking revelation that aliens can't reach us, through all the scientific barriers, through the philosophical implications, and finally to the understanding that this isolation is actually our greatest gift. But this isn't the end of the journey. This is the beginning. Because now you know, the universe is vast, but it's not empty of meaning. It's isolated, but that isolation is what makes consciousness precious. It's difficult to reach the stars, but reaching them is our responsibility. It's lonely out there, but that loneliness is calling us to become the civilization that transcends it. And you're part of that. You're part of something larger than yourself. You're part of consciousness reaching toward the cosmos. So here's my final call to action. Subscribe. Not because I want views though, I won't lie, I do. But subscribe because you've proven that you care about big ideas. You care about understanding the universe. You care about your place in it. And I want to keep you on this journey. In the coming weeks and months, I'm going to explore what this knowledge means for technology, for ethics, for how we should organize society if we're going to reach the stars. I'm going to talk about the future of consciousness, the possibility of other universes, the meaning of existence in a cosmos this vast and this lonely. But none of that happens if you don't stay connected. So please subscribe. And if you want to know more right now, if this video has opened questions that are burning in your mind, drop your thoughts in the comments. Tell me, does knowing that aliens can't reach Earth change how you think about the future? Tell me what insight hit you hardest. Tell me what you're going to do differently because of what you learned. I read the comments, seriously, and I respond. So let's continue this conversation. Let's think together about what the silence of the universe means for human consciousness. And one final thing. I asked at the beginning where you were watching from and what time it was. I meant that. Drop your location and time in the comments. I want to know that consciousness is scattered across this planet, across different continents, different time zones, all thinking about these cosmic questions together. That's beautiful. That's what makes us different from any other life form. That's what might make us unique in the universe. We think, we wonder, we reach for understanding. We ask questions that no other species we know of asks. And that's why, when the universe made us, it set us free to reach for the stars alone. Because consciousness is meant to question, to explore, to grow. And we're that consciousness. We're the universe becoming aware of itself. And our cosmic destiny awaits. Thank you for taking this journey with me. Thank you for believing that these big ideas matter. And thank you for being part of consciousness reaching toward infinity. Now go. Go out there and do your part. Be the change that takes humanity to the stars. We're watching. The universe is watching. And the future is waiting for what you'll do next.